So let's talk a little bit about apparent weight in circular motion. In order to do that, before we get to the circular, let's think back to just linear. So remember, we did a whole bunch of these elevators accelerating. And what we determined is that if you're in an elevator that's accelerating upward, then your apparent weight increases. You have an increase in apparent weight. So your weight apparent ended up being m times g plus the acceleration. Whereas if you're accelerating downward, then you feel your weight is decreased and your apparent weight is just mass times g minus the acceleration. And so let's see if we can get some analogy with linear motion versus circular motion. And in fact, we can, but we're going to do it anyway. So let's walk through it. So suppose you're in a roller coaster and you're going through a loop. So you're here in the roller coaster, upside down, strapped in. And what we want to know is what does it feel like? Now, if you've ever been in a loop, you know that at the top you feel less weight. So there's less apparent weight than, so, say, at the bottom. You know, you're coming through the bottom of a curve of a loop and you feel really heavy. You feel pushed into your seat. So what we're going to do is we're going to tie this off to centripetal acceleration. All right, so the way to do this is to think about the forces that are involved here. And since we're in circular motion, we know that there has to be a centripetal force acting downward in this case, and we'll have a centripetal force acting upward in this case. Okay, so let's think about the forces involved here. So I'm just going to sketch my force diagram off here to the side. So this is you, not the car, but you're being moved in a circle as well, right? The track is pushing on the car is pushing on you. So for you, you have some weight that's coming down. And then you also have a normal force pushing you. So you have a normal force pushing you in the same direction, and this is where it's key. So this is the normal force. And so both of these are in the same direction. And so we know that they have to be the net force. And so the net force, which is a centripetal force, is equal to your mass times, since it's a circular motion, the centripetal acceleration. Now my net force is just going to be the normal plus the weight. And that's going to be equal to mass times AC. Now remember that, I guess I didn't mention this here, that the apparent weight, apparent weight is the normal force. That's what the normal force is your apparent weight. So what we want to do is we want to solve for the normal force. So we get that the normal force plus your weight is always mg. It's apparent weight that we're looking for. Mass times centripetal acceleration. So I get that the normal force equals, so we move that over and we'll get MAC minus, oops, sorry about that. It's a subscript. AC minus mg. So the normal force, which is your apparent weight, is going to be, if I factor that out, it's mass times, let's go ahead and centripetal acceleration is just v squared over r minus g. So I factored out the mass. So that what I can see is I want to see this piece right here. So I can see that it's decreasing, that we're taking some off. We're going to get a, yeah, don't worry about these signs. I could have flipped it, mg minus mac. It doesn't matter. But the key is this. So my velocity has to be fast enough such that this amount is not zero, or else I'll have zero net normal force, and then I would just be falling, not moving in a circle. So the key here is going to be this piece right there. So this. If v squared over r equals g, then the normal equals 0 and we'll fall. So we need to know how fast we have to go. And this is our critical speed, they call it. So we could solve for that. So we would get v is going to be, I multiply r by g and take the square root. And this is the critical speed. If I'm going any slower than whatever this is, so it's only determined by the radius of the curve, if I'm going slower, I'm going to fall out. So this is this comes into play when you're swinging a bucket of water. You know, you have a rope with a bucket attached to it and has water in it, and you want to swing it around and not get it dumped all over your head. In order to do that, you have to swing it fast enough, and that's just determined by the radius. What's the radius? It has nothing to do with mass or anything like that. Because once that, if you're less than that, that's going to be a negative, and we can't have a negative normal. There's no such thing. That's not going to attract you and pull you up. All right, so let's look at, how about the bottom? So you should be able to determine, this one becomes less, so here we would expect that the normal force would become more, and in fact, that's what we'll see. So let's go ahead and do the same thing. So we're going to start with a force diagram. And again, we know our net force is up because we're coming around, and my acceleration is up, so my net force has to be up. Now you still have some weight. However, you're going to have enough normal force to counteract the weight and produce some centripetal force. So your normal force is much bigger than your weight at this point. So we can clearly see you're going to feel heavier. You're going to feel more apparent weight. But we can go through the same kind of analysis. So my net force centripetally is going to be the mass times the centripetal acceleration. And my net force, since they're in opposite directions, is going to be the normal minus the weight, is equal to mass times centripetal acceleration. So we get that the normal is going to be the weight plus MAC. So the normal, or your apparent weight, is mg plus MAC. And we get that the apparent weight on the bottom of the turn is your normal force, which is going to be m factored out, g plus AC. And see, we get the same thing. It's this kind of relationship. It's the same exact thing. Okay, so we subtract, right here we'll subtract the accelerations. When we're at the bottom, we end up adding them. And that's it. So you also need to know about centrifugal force and how that does not exist. So don't ever write it, don't talk about it, unless you're saying that it doesn't exist. So if you say centrifugal force, you have to immediately say centrifugal force, which does not exist. Okay, that's it.